Right, well, yeah, thank you for the invitation. Okay, so today's talk is going to be about, I'm going to be speaking about a number of classification problems in low-dimensional topology, and particularly classification problems for which there are sort of algebraic obstacles. And my work is largely on trying to overcome these algebraic obstacles. So the first classification problem I will talk about will be the classification of two-dimensional cell complexes, or equivalently group presentations up to homotopy equivalence. I'll then talk about the related problem of classification of four manifolds. And this is sort of related in the sense that it's, in some sense, you could view it as analogous. So in terms of the classification of four manifolds up to homotopy equivalence, at least. And also there are applications of the classification of two complexes to four manifolds via a particular construction. So, right. And before I launch in, I'll just say that this work is sort of based off of a couple of preprints. So the first part is sort of reducing the topological problem to an algebraic one. And the second one is solving that algebraic problem. And this is based off of some previous work of mine from the year before, which was focused more on the Detour problem of Terry Wall and a certain problem about cell structures of Poincare through complexes. So this is sort of applying those methods to these more general problems of homotopy classification. Okay, so I'll start by talking about the homotopy classification of two complexes. So what do I mean by two complex? So a two complex I'll take to mean a finite connected two-dimensional CW complex. And I'll just recall the following construction, which people have probably seen before. So, but I'll just recall it nonetheless. So for a finite presentation P of G, and by finite, I mean finitely many generators, finitely many relations. You can let XP denote the presentation complex for P. So presentation complex is the complex which has a single zero cell, a vertex, and it has a one cell for each generator of the group, and then a two cell for each relation. So the idea is you glue the relations, you glue the two cells, you glue the two cells on their boundary alongside, along how the relation is written in terms of the generators. And the picture looks something like this in general. Okay. And so this gives you some examples of two complexes, but actually it turns out that this gives you everything. So up to homotopy equivalence. So in particular, the proposition is that if X is a two complex with fundamental group G, then there always exists a presentation P for G, such that X is homotopy equivalent to the presentation complex for P. And how is this proven? The idea is you basically take an arbitrary two complex, and you can always find a spanning tree of the vertices. And if you contract that spanning tree to a point, you get a homotopy equivalence from X to a two complex with a single zero cell. And a single zero, two complex with a single zero cell is kind of equivalent to a presentation in the data that it makes up, and so corresponds to one. Okay. So for the purposes of this talk, I'll sometimes switch back and forth between talking about two complexes and talking about group presentations, because they're basically the same thing up to homotopy. Okay, so then I'll ask the basic question, which is, how do we classify two complexes, i.e. group presentations up to homotopy equivalence? Okay, and this gives you sort of, in some sense, a natural classification problem on group presentations. So there's many other ways in which you can classify presentations, but this gives you a particular way which sort of comes from the topological perspective on what a group presentation is via the last proposition. Okay, so and then the first basic question, the first basic fact when you're trying to classify two complexes is the following. So suppose you have two complexes, X and Y, which have the same fundamental group G. Then there always exists A and B, such that X and Y are homotopy equivalent after a wedge with a number of copies of S2. So when I say A times S2, I mean S2, the two sphere wedged A times. And so recall, so what this basically means is, so recall what I mean when I say wedge product, just in case people have forgotten, is you take a two complex X, and then you take the two sphere, and you're essentially just attaching them at a point to get a new two-dimensional cell complex. So what this really says is, if you take two complexes, you can kind of add a number of pinpoles to one and add a number of pinpoles to another, and these things become actually homotopy equivalent. Okay, right. And this reduces the classification of two complexes to the following. So known as a cancellation problem. So if X and Y are homotopy equivalent after a wedge with S2, then does this imply that they're homotopy equivalent? And this almost seems, if you try and picture two complexes, it kind of feels like that should obviously be true. But actually, it turns out that it's not true. So when you wedge on a copy of S2, you get these kind of really bizarre automorphisms up to homotopy of the space, for example. There's a lot of weird things that can suddenly happen. Okay, and just to introduce a piece of terminology, which is sort of relating to the title of the talk. So we say that two presentations P and Q for a group G are exotic presentations if their corresponding presentation complexes have the same Euler characteristic, but the presentation complexes are not homotopy equivalent. And what this basically means, since wedging with a copy of S2 adds 1 to the Euler characteristic, this is the same as saying that these presentation complexes are isomorphic after some number of wedges with S2, but are not homotopy equivalent to begin with. Okay, so you can say that these presentations are in some sense stably isomorphic, but not isomorphic. Okay, and I'll just note that this condition about the Euler characteristic of the complexes, this can be viewed in purely group theoretic terms. So it's the equivalent thing to say is that the deficiencies of the presentations are equal. So that is the number of generators minus the number of relations. Okay, so how do we solve this cancellation problem is sort of one of the main topics of the talk. Okay, so I've mentioned exotic presentations. Let's give some examples. So the first example will be for finite abelian groups. So suppose you have Z mod M1 all the way up to, with direct product all the way up to Z mod Mn for some integers Mi. Then you can write down the following presentations. And you note that if I take, so for any integer R which is co-prime to M1, and you note that if I just take R is equal to 1 there, that this is essentially just the standard presentation for the finite abelian group. So what I'm really doing is I'm sort of just twisting this presentation by raising, one of the relators, raising one of the generators to the power of R. It turns out this still gives another presentation. Okay. So now if I just assume that these are all sort of in order of divisibility, which you can kind of do by Smith normal form, etc. Then we have the following theorem. So the theorem is that these two presentation complexes will be homotopy equivalent if and only if R times S inverse is equal to 1 in this thing. So in other words, they're homotopy equivalent if and only if R and S differ by plus or minus 1 times an n minus 1th power. Okay, and this leads to examples of exotic presentations. So an easy example, and rather the smallest example, is the group Z mod 5 cubed. So in this case, n is equal to 3. So you need two things that don't differ by plus or minus a square mod 5. And in this case, you can take these two presentations. The first one is sort of the case R equals 1, P1. The second case is P2, and this comes from the fact that 2 is not plus or minus 1 times a square mod 5. Okay. So these are our first examples of exotic presentations. And these were found by Wolfgang Metzler in 1976. The above theorem was sort of generalized later by Alan Siradsky. Okay, and there's another theorem, which I'll mention, which comes from Browning, Wesley Browning from 1976, which is that actually every 2 complex whose fundamental group is finite abelian is homotopy equivalent to one of these presentation complexes wedge a number of copies of S2. So in particular, this theorem, or rather the combination of these two theorems, sort of leads to a complete classification of presentations or finite 2 complexes over finite abelian groups. Okay, so really it's just these presentations and adding on wedging S2, and wedging S2 on presentations just means sort of adding a trivial relation, for example, adding 1 many times. And these are essentially all the presentations up to homotopy. Okay, some more examples. So the trefoil group, i.e. the fundamental group of the complement of the trefoil knot in S3. This has the following presentations, Pi. And we note that in the case I equals 0, this presentation, if you just plug in I equals 0, it sort of reduces just down to this presentation. So x generated by x and y with the relation x squared equals y cubed. is sort of the sort of well-known standard presentation for the trefoil group. Okay. And it was proven, so in combination with results of Berridge Dunwoody in 1979 and Harlander Jensen in 2006, it was proven that there is an infinite subset of the integers on which all of these presentations are sort of pairwise exotic presentations. So the presentation complexes are all homotopy equivalent after you wedge with, in this case, actually just a single copy of S2, but none of them are homotopy equivalent. And this sort of combined algebraic results in 1979. But actually, yeah, I mean, maybe it's a bit hard to explain, but yeah, there were sort of algebraic results which suggested that there would be these exotic presentations, or infinitely many, for the trefoil group in 1979. But the presentations themselves, these ones I list above, weren't actually found until 2006. So I think Dunwoody managed to find the first one, P1, and he wrote a paper sort of giving those presentations first. Okay. So yeah, so I've gone through two examples. There's actually, yeah, so the point I'm trying to make is actually there aren't really many other examples. Okay, so there's similar examples obtained by Martin Lustig as well as Harlander Jensen for some related infinite groups. But other than these, as far as I know, these are really the only known examples. Okay, so yeah, really I've given you pretty much everything. So and this is one of the issues in the subject, is that it's the proofs that these things are actually exotic presentations. You run into sort of quite severe algebraic difficulties, and so consequently, there sort of not really many other examples have been found. Okay, right. So now I'll go on to something else. So I'm going to talk about the homotopy classification of four manifolds.
Sorry, John, I have a question.
Yeah, sure.
Are there examples of groups which don't have exotic presentations?
Yes, yeah, there are. So there's been a lot of work done on that. So for example, finite subgroups of SO3 have been proven by Ian Hambleton maybe 2 years ago, that none of them had exotic presentations. Okay. And there's other cases that I'll discuss here.
All right, great, thanks.
And yeah, families of infinite groups like the integers times a cyclic group, finite cyclic group, for example. There's a lot of like ad hoc results where it's known that there aren't exotic presentation. Okay, so on to four manifolds. So by four manifold, for the purposes of this talk, I will, all four manifolds will be smooth, orientable, closed, connected. Okay, so without further mention. Okay, so definition is, I'll say two four manifolds M and N are stably isomorphic if they're going to be isomorphic after you connect some with A copies of S2 times S2. Okay, and what do I mean by isomorphic? There's many choices that you can make for the notion of isomorphism. You could consider them up to diffeomorphism, homeomorphism, or homotopy. And of course, if we're considering them just up to homeomorphism or homotopy, the manifolds need not be smooth, but I'll just consider the smooth case in this talk for simplicity. Okay, so this is a little bit analogous to the situation for two complexes that I said before. So for two complexes, you can take a wedge with S2, and if you do this, then any two complexes with the same fundamental group become equivalent just with this wedging operation. So is that the case for four manifolds? Do four manifolds with the same fundamental group become equivalent after this connect sum operation? Which, noting this connect sum operation, since S2 times S2 is simply connected, does preserve the fundamental group again. And the answer to that is no. So, if you have four manifolds M and N with the same fundamental group, then they're not necessarily stably isomorphic. Okay, so the situation is not quite as simple as for the case of two complexes. But nonetheless, so the stable classification can be often reduced to a Bordism problem. And when I say often, I mean given some restrictions on the fundamental group, and can therefore be solved using tools from algebraic topology. So this is partly the idea of correct modified surgery, for example. And there's been a bunch of recent papers over the last 10, 20 years where there's been, with different assumptions on the fundamental group, people have been able to classify four manifolds up to stable isomorphism. Okay, so given this, and given that we have situations where there's a stable classification, in these cases, at least. This reduces the classification of four manifolds to the following problem, which is another cancellation problem. So if two four manifolds are isomorphic after a connect sum with S2 times S2, then does that imply that the four manifolds were actually isomorphic to begin with? Okay. And in this talk, we'll just be interested in the cancellation problem up to homotopy equivalence. And note that the classification problem up to diffeomorphism is sort of one that people will probably know quite well, but by another name. This is namely, the situation of having exotic smooth structures on four manifolds. So there's a theorem about if you have two four manifolds which are homeomorphic, but not diffeomorphic, then they actually become diffeomorphic after a connect sum with a number of copies of S2 times S2. So the question of whether or not two homeomorphic manifolds are diffeomorphic is actually a cancellation problem, with a cancellation problem up to diffeomorphism. Okay, right. So how do we do it up to homotopy? So we have the following theorem. So I've said it's the theorem of Donaldson. It's really a theorem that follows from Donaldson's theorems, which is that if M and N are simply connected four manifolds, and I'll write smooth here just to emphasize in case people have forgotten. If we have simply connected four manifolds, then if they are homotopy equivalent after a connect sum with S2 times S2, they are homotopy equivalent after connect sum with S2 times S2 if and only if they are homotopy equivalent. So in particular, we have this kind of cancellation theorem in the case of smooth four manifolds up to homotopy. And how do we prove this? I won't actually give details, but the idea is basically simply connected four manifolds of any type are determined up to homotopy by their intersection forms. In the case of, if the intersection forms are indefinite, then they are determined by their rank, signature, and type. If they are definite, then Donaldson's theorem implies that the forms are of a standard type and therefore also are classified by their rank, signature, and norm. And rank, signature, and norm are sort of respected by this connect sum operation, and so, well, not respected, but yeah. So it follows from those results. Okay. So in light of this, in order to study this problem, the cancellation problem I discussed over here, we really need to focus on non-simply connected four manifolds if we're to find examples of non-cancellation, for example. So we really need a good supply of these types of manifolds. And the following construction is particularly useful in constructing non-simply connected four manifolds with prescribed fundamental group and certain properties. The construction is the boundary of thickenings construction. It's often known as the doubling construction because of another interpretation. And the construction is, so if X is a two complex, then you can always find a homotopy equivalent simplicial two complex, X naught, and once you have a simplicial two complex, it always has an embedding into R5. Okay, and you can then take the boundary of this, you can then take a smooth tubular neighborhood of this embedding and then take which gives you a five-dimensional smooth manifold with boundary. And if you then take the boundary of that kind of regular neighborhood, that now gives you a four manifold. Okay, so I don't want to get into the minor details of checking everything in the construction, but this basically gives you a kind of a funny way to construct four manifolds from a two complex. Okay, so you take a two complex, embed it into R5, and then take the boundary of this thickened tubular neighborhood. Okay, so yeah, what sort of uniqueness do we have for this construction? So it turns out that, if you differ the two complex by not a homotopy equivalence, but a simple homotopy equivalence. So I don't really want to get into these details too much, but the point of a simple homotopy equivalence is a homotopy equivalence that can be broken down into certain simple steps, such as taking a thick ball and contracting that. And it turns out that if you differ the two complex by a simple homotopy equivalence, that you just change the corresponding four manifold by an Escobar-ism. And Escobar manifolds are homotopy equivalent. So this gives you a kind of a way to take two complexes unique only up to simple homotopy equivalence, which is a detail we can deal with another time, and you get a four manifold which is unique up to homotopy equivalence. Okay, and this enjoys a couple of nice properties. The first one is that the four manifold you get has the same fundamental group as the two complex you started with. And the second one is that this actually respects this operation. So this gives us a, rather before I just sort of pulled these two notions out of the hat and sort of declared that they were analogous. This gives you a kind of a reason why it makes sense to think of them as analogous. So namely, if you wedge the original 2 complex with a copy of S2, and then you pass to the boundary of thickening, then this amounts to connecting sum with a copy of S2 times S2. Okay. So there's a few details here, but we really just need to think of it as a way to construct 4 manifolds from 2 complexes. Okay. And the question we can ask is, if we have two complexes, which are simple homotopy equivalent after a wedge. So suppose we have two complexes, which are simple homotopy equivalent after a wedge, but not homotopy equivalent. Then this will imply that the corresponding 4 manifolds, M of X and M of Y, are homotopy equivalent after a connect sum with S2 times S2. So we can ask the question of, is it the case that M of X and M of Y are homotopy equivalent? Maybe this is a way to give examples where M of X and M of Y are not homotopy equivalent, for example. And yeah, this detail about simple homotopy, when I say you can get rid of it easily, so there's nice theorems. So for example, if you have, if your 2 complexes X and Y have a finite fundamental group G, then it turns out that being simple homotopy equivalent after a wedge is exactly the same as being homotopy equivalent after a wedge. So for the situation of finite fundamental group, it's the same thing. And that follows from a theorem of Hamilton and Craig in the 90s. Okay. So yeah, and so indeed this procedure was carried out by Craig and Schaefer in 1984. And they basically took these presentations for finite abelian groups, PR, the ones I mentioned before, and they basically showed that there exists some numbers R and S, and for some MI as well, for which these things are not homotopy equivalent. Okay. So the answer to this is that there's some cases where this is the case. Okay. So a few remarks on this. So the first one is that actually these are the only known examples of 4 manifolds M and N, which are homotopy equivalent after connect sum with S2 times S2, but are not homotopy equivalent. Okay, so I mean, this is as far as I know. I mean, I haven't been able to find any, and I've spoken to people that they don't know of any others. But yeah, so I found this quite surprising, because you'd think there's a lot of different constructions flying around, like surely there will be another way to find these examples. But in fact, I'm pretty sure there isn't. So and the whole reason for this is that finding examples of things which are 4 manifolds in particular, which are stably homotopy equivalent but not homotopy equivalent is kind of just a very subtle business. There's a lot of assumptions on the fundamental group, for example, which would ensure that this is the case. Well, you'd expect. And it's the algebra involved is sort of becomes quite subtle. In fact, so the calculations involved in the paper of Craig Schaefer are sort of so difficult that they can only really prove that they're not homotopy equivalent in a few cases. And to do this, they really throw sort of every tool in the book at it. They use algebraic L theory. They use quite a lot of things to get this result. And in particular, there's many cases of finite abelian groups which aren't of complexes, of this form, which aren't homotopy equivalent, but it's not really clear from their results whether or not the corresponding 4 manifolds are. Okay. And in particular, there's no known examples where X and Y are not homotopy equivalent, but then the corresponding 4 manifolds do become homotopy equivalent. So sort of the orthogonal result. Okay. And this motivates further work, I believe, on the cancellation problem for 2 complexes. So are there maybe other results that you can get for 2 complexes which make these kind of considerations a little bit easier? Other situations where you can find simpler examples with simpler algebra, for example. And there's also a number of open problems in this direction. So, for example, if you take the second homotopy group of these 4 manifolds, which you can consider as a module, so it's not known if if these modules can be different, for example, for these manifolds M and N. So there's a lot of things unknown, which come from the fact that these are the only known examples, basically. Okay, right. So that gets us past the sort of preliminaries. So I've spoken about 2 problems now, 2 complexes and 4 manifolds. What will our aim be for the rest of the talk? So the aim for the rest of the talk will be to partly will be aimed at the specific case of groups. Okay, so a group G has 4 periodic cohomology if its tate cohomology groups are basically 4 periodic. So if it satisfies this for all I. And what are the tate cohomology groups? These are basically things that for positive I are just your normal group cohomology groups, but they do also extend into the negative I, where they become the group homology groups. Sort of a weird patchwork definition. Okay, but we won't actually need this definition. All we need to bear in mind is that such a group is necessarily finite, and that this period I must be even. And the following proposition, which gives you a nice way to construct, a nice place that these groups comes from. So in particular, if M is a closed 3 manifold whose fundamental group is finite, then G always has 4 periodic cohomology. Okay, and this also works as well if you sort of loosen the definition manifold. So if 3 manifolds are replaced with 3-dimensional Poincare complexes, which are just CW complexes with a sort of, for which Poincare duality holds in homology, then this also holds as well. Okay. And for example, so, we know the case of, probably people have seen the case of lens spaces before. So we know cyclic groups can arise as the fundamental groups of 3 manifolds. In particular, the cyclic groups therefore have 4 periodic cohomology. But if you actually compute their cohomology, it turns out that it's actually 2 periodic. Okay, so maybe if we defined it as I didn't define it as the minimum period, but yeah, if you defined it as the minimum period, then this would say that G has period dividing 4. And another example, which is one I'll come back to later, is the case of quaternion groups Q4n, which are fundamental groups of 3 manifolds. Quaternion group Q4n for n at least 2 always has 4 periodic cohomology. So this is the group of order 4 for n, and in the case n equals 2, this is just the usual quaternion group of order 8. Okay, and our main results will concern cancellation problems for 2 complexes and 4 manifolds in the case when G has 4 periodic cohomology. Okay, so now I'll start working my way towards the main results that I'll state. Okay, so I'll begin with an algebraic model for 2 complexes. So some background on what sort of things you need to do in order to actually classify 2 complexes up to homotopy. So the first thing I'll say is just to give another definition. So a polarized 2 complex is going to be a pair of a 2 complex X and an isomorphism rho, where rho is sort of an isomorphism from pi of X to a fixed group G. Okay, so fix a group G. Fix an abstract group G, and then if you have a 2 complex whose fundamental group is G, then you can get this polarized 2 complex where you also remember the explicit isomorphism of the fundamental group. Okay. So suppose we have 2, and so we can extend the notion of homotopy equivalence to polarized 2 complexes as well. So suppose X rho X and Y rho Y are, we say that these 2 complexes are polarized homotopy equivalent if there exists a homotopy equivalence between Y and X, which essentially satisfies this identity on the polarizations. So namely, you have a homotopy equivalence that induces a map on the fundamental groups, and you want the map that it satisfies to satisfy this basically. And that essentially just means that if you pull this map back to, so this is a map from pi1 of X to pi1 of Y, and if you use the polarizations to express it as a map from G to G, then that map will just be the identity. Okay, so maybe I haven't explained this quite well. There's a lot of words. Okay, right. So then I'll just introduce some notation. So if I let PHT of G2 be the set of polarized 2 complexes X rho up to polarized homotopy equivalence. Okay. So in other words, you can just think about this as 2 complexes with a fundamental group G, and we're considering them up to homotopy equivalences which induce the identity on the fundamental group, in other words. And this gives us a general idea to classify 2 complexes with fundamental group G. The first step is to classify up to polarized homotopy, i.e. determine this set PHT of G2. And the second step is to then determine how altering rho by an element of the automorphism group of G will actually affect the polarized homotopy type. So we can think about this as a sort of depolarization. Okay. And, so why does this make sense to do at first? Basically, the whole point is that it's easy to compare two complexes with the same fundamental group if you identify those groups first. Okay, is there any questions up until this point? No? Okay, good. Right, okay, so for a group G, I'll also let ZG denote the integral group ring. And so by ZG, I just mean the sums, the linear combinations of group elements with integer coefficients. So, and I say, yeah, so in case the group is infinite, I'll say that these coefficients are going to be 0 almost always, i.e. they're going to be only non-zero on a finite set. Okay, so these are finite linear combinations of group elements which form a ring in a natural way. Okay, and note that ZG modules are just exactly the same thing as a G module, so, which you may have seen in other contexts. So in particular, you can just, the action of, so when you define a module, like you need an action of ZG on an abelian group, which is a sort of a ring action, but this is just the same data as an action of a group on the abelian group. So ZG modules are basically just an abelian group with a group action on them. Okay. And we'll also assume that ZG modules are finitely generated left modules from now on as well. Okay, so why am I talking about modules? So they arise in the following way. So if X is a 2 complex, then, and yeah, noting that I assume it's connected, etc. Then since the zeroth homology of the universal cover is Z, by taking the cellular chain complex of the universal cover, we basically get the following exact sequence of abelian groups. Okay, and when you have so exact sequences of this kind, you kind of call a resolution. Okay, and instead of just being an exact sequence of abelian groups, since we have the universal cover, this has an action from the fundamental group pi1 of x by monodromy. And in particular, since this action is free on the cells, or we can assume that the action is free on the cells, these cellular chain groups rather are actually going to be free Z pi1 of x modules under this action. Okay, and also, so now this is where the polarization comes in. That if we have a polarized 2 complex, then we can use our polarization to actually convert C tilde star of x into a chain complex of ZG modules. Okay, so we can just replace, so this isomorphism, pi1 of x to G gives you an isomorphism on the group rings, and this gives you a way to, map Z pi1 of x modules to ZG modules. Okay, so in particular, this thing is a chain complex of ZG modules. So what have we actually done here? So we can express this all in very simple terms in terms of a map just between sets. So there's a notion of an algebraic 2 complex over ZG is just going to be a chain complex of free ZG modules, Fi, where it gives an exact sequence Fn to F1 to F0 to Z to 0. Okay, so this is an algebraic 2 complex, and we will let algebra G2 be the set of all of these things up to chain homotopy equivalence. Okay, and so what we've actually shown via the previous construction is actually just that we have a map C tilde star from the set of polarized 2 complexes to the set of algebraic 2 complexes. So in other words, XP just maps to this this resolution, which we then use this map rho to convert it into a sequence of ZG modules. Okay, and there's a theorem which is that this map, this function, is actually injective. Okay, so bearing in mind polarized PHT, this is 2 complexes up to polarized homotopy equivalence, and this is up to chain homotopy equivalence. So when we say it's injective, we basically just mean that two complexes are polarized homotopy equivalent if and only if their corresponding chain complexes are chain homotopy equivalent. And in other words, this is basically saying that it gives you a complete invariant on the homotopy class of the 2 complex. Okay, and we can ask the following question, which is this map actually bijective? So is it the case that every algebraic 2 complex is geometrically realizable? Does every exact sequence of this form arise as, as the cellular chain complex of a 2 complex? Right. So now I'll get on to talking about Wald's Detour problem, which is an old open problem from the 1960s that sort of links in with this story quite well. So a DN complex is a finite connected CW complex X with basically whose cohomology in dimensions above n vanishes with respect to all z pi 1 of x modules. And you also have this other condition that the homology groups of the universal cover also vanish, which is also follows from the stronger condition that all of the homology groups of x with all coefficient modules m also vanish. Okay, so this is something that's, so what is a DN complex? So certainly every n-dimensional CW complex will satisfy this property, given that it's n-dimensional. And so it's really the question of like, is every DN complex actually homotopy equivalent to an n complex? Okay, so, and this was a question asked by Wall in 1965. And what he proved was that actually the answer is yes for n at least 3. So every for example, every D3 complex is i.e. any finite complex with these conditions is actually homotopy equivalent to a 3 complex. And it was also proven in the case n equals 0 with a combination of work of Stallings and Swan in the 1960s, just following Wall's work. And the case n equals 2 just remains completely open. And this is known as Wall's Detour problem. Okay. And one way to talk about Wall's Detour problem is with the following definition. So we say that a group G has the D2 property if every D2 complex X whose fundamental group is G is homotopy equivalent to a 2 complex. So in other words, with this definition, Wall's Detour problem basically just says, does every group G have the D2 property? Okay, and there's no known examples of a group which doesn't have the D2 property. It's conjectured that there will be one, but people haven't really been able to find one. And it's been, I guess, nearly 60 years now. Okay, an important case of the D2 problem, and linking in with the talk, is the case where G has 4 periodic cohomology. And I believe this is important for the following 2 reasons. The first one is that they've been the source of many proposed counterexamples. So for example, Cohen, Johnson, and Bale and Waller across the span of many years have proposed counterexamples in this family. And the second is that they have applications to the following question, which is, does every Poincare 3 complex have a cell structure with a single 3 cell? So noting that this is true for 3 manifolds using Morse theory. So every 3 manifold has a cell structure with a single 3 cell, but this is still unknown for Poincare 3 complexes. This has been unknown since 1976. And this was explored by my supervisor, Frank Johnson, in 2000, and also by myself in the first of my papers in 2019. Okay. Right. So how does the D2 problem relate to this classification that we're considering? So it turns out that we have the following, which is that every algebraic 2 complex over ZG is geometrically realizable if and only if G has the D2 property. This was shown by Johnson for all groups, just subject to a few kind of minor conditions, which were later shown to be not important by Manon in 2009. So in particular, what we have is that the injective map from polarized 2 complexes to algebraic 2 complexes is bijective if and only if G has the D2 property. Okay, so we can study about when this map is injective, is bijective, and infer the D2 property or do the converse. Okay, so to summarize everything, so there's a lot of detail there. We need to just take away the following 2 things. So the first thing is that algebraic 2 complexes give you a kind of an upper bound for polarized 2 complexes. But there may nonetheless be algebraic 2 complexes which cannot be realized by 2 complexes. Okay, right. So another ingredient which will go into the theorem.
Sorry, by upper bound you mean as a like you mean there's just this injective map? Yes,
exactly. Okay. Exactly. Yeah, exactly. So if so for example, you could classify all algebraic 2 complexes and you know very explicitly, and you know that polarized 2 complexes are somehow just some subset of these things. Yeah. Okay, so another ingredient that goes into my main theorem is projective modules over integral group rings. So what are these things? So there's many definitions of projective. My favorite one is the following, which is just that P, a ZG module, is projective if there exists another ZG module Q, such that P plus Q is a free module of some finite rank. Okay, and if P naught is a projective ZG module, then we let brackets P naught be the set of all projective modules P which are stably isomorphic to P naught, where in this case stabilization means adding a copy of the free module ZG. Right, so maybe you could see how this sort of relates to some of the things we were talking about before already. So we have yet a third notion of stabilization. Okay, right, and yeah, of course we now have a third cancellation problem, which is when does this class P naught have cancellation? I.e., if we have if P and Q are projective modules which are isomorphic after adding a copy of the free module, then does this imply that the modules P and Q are themselves isomorphic, restricted to the case where the P and Q are projective modules in the class P naught? Okay, and a simple example is the following case, which is when P naught is just the free module itself. So bracket ZG is just all the projective modules P for which P plus ZG to the I is isomorphic to ZG to the J for some I and J. In other words, it's the set of modules which are stably free. So they're free after some notion of some stabilizations by a free module. Okay, and in particular, ZG has cancellation if and only if every stably free ZG module is free. Okay.
Can I?
So the question, yeah.
Sorry, can I ask a potentially dumb question? But what does projective have to do with this cancellation problem?
With this one?
Yeah. Why can't you? I mean, surely you can make the same question for modules in general.
Yes, yeah, you definitely can make the same question for modules in general. Yeah, but I guess we'll see where this particular problem arises. Okay. So yeah, it's definitely still interesting. Other cases where P naught is not projective, definitely still interesting. Yeah. Okay. Good question. Okay, so now I get to my main results, which hopefully people can remember some of the, there's a lot of technical preamble, I guess. Okay, and yet one more piece of technical preamble, which is that if we let E be an algebraic 2 complex, then we can define E plus ZG, E plus a free module, or a stabilization of the algebraic 2 complex, to basically be the algebraic 2 complex you get by just adding on a free module ZG to the term F2 and mapping it by 0 to F1. Okay, so with this, we have the following theorem. So, and this is from sort of part A of the 2 papers I mentioned. So if we let G have 4 periodic cohomology, then the theorem is that there exists a projective ZG module, a special projective ZG module PG, and a bijection of the following form. So it's a bijection between the class of algebraic 2 complexes over ZG and this class of all projective modules stably isomorphic to PG. And the map is sort of like a nice map in the sense that psi of E plus ZG is isomorphic to psi of E plus a free module for all algebraic complexes. Okay, so this gives us a way into the problem all of a sudden, because it gives us a way to actually determine algebraic 2 complexes just by studying projective modules instead. Okay, and in particular, if we compose with our cellular chain map, this tells us that G has the D2 property if and only if the map from polarized 2 complexes to PG is bijective. Okay, so this gives us a way, like if we can take a group G and we can figure out everything about its projective modules, maybe we could approach this question about whether or not G has the D2 property. Maybe we can classify 2 complexes as well. Right? Okay, and the second result is the following. So now I'll consider the depolarization. So suppose let HT of G2 just be all 2 complexes with fundamental group G up to homotopy, not just polarized homotopies. And note that this is recovered from the polarized case by quotienting by an action of the automorphism group Aut G. And in particular, the idea is you can just, you can take one polarized complex X row to another by just by composing the polarization with an automorphism of the group G. Okay, and by doing this, you can actually just get between all of them and therefore the quotient by this action actually recovers you the original two complexes up to homotopy. Okay, so with that we have the following theorem, which is the depolarization part. So let G have four periodic cohomology, then psi induces an injective map from the two complexes up to homotopy to the projective modules in the class PG, quotiented by the action of ORT G. Okay, and this satisfies the nice structural relation that when you wedge with a copy of S2 for the two complex, then your corresponding projective module, you just add a copy of the free module ZG. Okay, and this is for some action of ORT G on PG. Okay, and this is bijective, sort of by the previous discussion, if and only if G has the D2 property. Right, so this is in some sense the thing that we need to compute in order to study this problem. And you'll note, if you're paying attention really closely, you'll note that this kind of almost doesn't really have any more content in than the previous thing, because, you know, what is the ORT G action? You know, if you just take the induced ORT G action, then you get this theorem from the previous one sort of immediately. But the point is that this ORT G action is a very specific one that I can give, yeah, but I won't give, basically. And there's a remark about this action, which is that there is actually an obvious action, or sort of a natural action of the automorphism group on the class of projective ZG modules. So namely, if theta is an automorphism of the group, you can do the following. So if P is your projective, then you can form a new projective P theta, which is basically a projective module with the same abelian group as P, but with the action sort of twisted. So when previously you would multiply X by G, now you multiply it by theta of G. Okay, but however, our action is a priori more complicated than this one. So this action of ORT G on PG is not necessarily that one. Though I sort of confess that I don't actually have any examples where this action of ORT G on PG is not that action. And yeah, the weird thing is basically to do with the fact that this action on projective modules doesn't necessarily restrict to, you know, it doesn't necessarily map something in this class to something in this class. You act by this theta, and then you have to pull back by something. And whether or not the thing you need to pull back by is just the trivial thing sort of relates to some open problems in, you know, in the subject from the 70s and 80s, which haven't been resolved. So that's a weird thing. But it gives you some kind of indication of the richness of these problems. Okay, and so that's the results from you know, the sort of reduction to topology. Now there's the second part of the results, which is sort of resolving the algebraic problem. So how can we resolve the algebraic problem? So I need a few preliminaries here. So if G is a finite group, so and remembering all groups with four periodic cohomology are finite, then recall that we always have a decomposition of the real group ring Rg as the product of matrix rings over division algebras, real division algebras, which always have to be just Rc or the quaternions H. Okay, so everything has this decomposition. This corresponds to the real representations of the group G. And I'll make a definition, which is MH of G, to denote the number of copies of H that occur in this decomposition. So we're not allowing like M2 of H, 2 by 2 matrices over H. It's just the number of copies of 1 by 1 matrices over H that occur. So for example, for the quaternion group of order 8, RQ8 is R to the 4 times H. So you have 4 one-dimensional real representations and 1 one-dimensional quaternionic representation. And this, therefore, you know, MH of Q8 is 1. The number of one-dimensional quaternionic representations is 1. Okay, and we say that G satisfies the Eichler condition if MH of G is 0, i.e. if there are no one-dimensional quaternionic representations. And this is relevant to figuring out the cancellation problem for projective modules because of the following result, which is from Jakubinski in, I think, maybe sometime in the 1960s. He says that if G satisfies the Eichler condition, then the class of P has cancellation for all projective modules ZG. So, for example, in the case of stably free ZG modules, this implies that every stably free ZG module is free. Okay, and I'll just note that the cancellation problem for P when G does not satisfy the Eichler condition was studied systematically by Richard Swan in the 1960s to 80s. And so in theory, so since since the case, so it turns out the case of groups with 4 periodic cohomology, many of them don't satisfy that isolate condition. So in order to determine, going back quite quickly, in order to determine when this class has cancellation, and hence determine the cancellation problem for 2 complexes, it should suffice to just plug in all the groups with 4 periodic cohomology into the results of Richard-Swan. However, unfortunately, you can't do that because the results of Swan aren't sufficiently general to include those cases. So therefore, I had to write some more papers. I had to solve this problem myself. So it became the project kept growing, basically. And so what are my main algebraic results? So by extending Swan's results, I managed to show the following. So the first theorem is if G has 4 periodic cohomology, then the following are equivalent. The first is that PG has cancellation. The class of the projective module is PG. The second one is that it has cancellation when you quotient by the action. So this is kind of a nice thing. The action sort of doesn't matter when it comes to cancellation, even though the action is non-trivial, you can show. And this occurs if and only if you have at most 2 quaternionic representations in the group. Okay. And by the way, so I didn't mention before, so this projective module, it's a very, very specific thing. It's, in case anybody knows about this kind of stuff, it's actually it's equivalent to the wall finiteness obstruction for a Poincare complex, Poincare 3 complex with fundamental group G. It determines whether or not it arises as a certain obstruction in topology. It's a very explicit, specific thing. The Swan finiteness obstruction, it's often called. Okay, and the second result, so this one basically determines when cancellation occurs precisely. But what about in the case where MH of G is very large? How badly does cancellation fail in those cases? So that leads me to the second result, which is that if M is the number of one-dimensional quaternionic representations, then the number of non-cancellation examples, so the number of P such that P is stably isomorphic to PG, even quotiented by ORT G, is basically this really, really massive thing. So it's a super exponential number in the number of quaternionic representation. Okay, so absolutely enormous. And of course, this kind of proves this for M sufficiently large. So M sufficiently large, this thing will be greater than 1. It's greater than 1 if MH is at least 3. If MH is very large, it's enormous. Okay, so sorry, I'm pushing up against the time. I'll try and get through to linking back to the problems that I mentioned at the start. Okay, so what's the consequences for homotopy classification of 2 complexes? So recall that we found this injective map from 2 complexes onto this class of projective modules, which was bijective if and only if G had the D2 property. What can we show using our results? So we can show the following. Firstly, if MH of G is at most 2, then 2 complexes over G have cancellation, i.e. there does not exist any exotic group presentations for G, which is sort of something someone asked about earlier in the talk. And note that we don't need the D2 property for this because this map is injective, so that we know there's an injective map into something which has cancellation, and therefore 2 complexes have cancellation as well. The second thing we can prove is that if MH of G is at most 2, then G has the D2 property if and only if there exists a 2 complex with fundamental group G and Euler characteristic 1. And this is equivalent to saying that there exists a balanced presentation for the group G, a presentation with the same number of generators and relations. And this essentially amounts to, if MH of G is at most 2, then this thing has, this thing on the right has cancellation. So we have 2 things which have cancellation, and this is just about determining the minimum level. Are there, do 2 complexes exist that hit the projective modules of minimum rank? If that doesn't make sense, then don't worry. Okay. But perhaps what's even more interesting is the case where the number of H's is at most 3, is at least 3 rather. So the first corollary is that if MH of G is at least 3 and G has the D2 property, then this tells you that HT of G2 fails cancellation. In other words, there exists 2 complexes which are equivalent after a wedge, but not homotopy equivalent. So in other words, if you have the D2 property, then you always have exotic presentation. Okay. And the second thing is we can use our bound in the case where M is very, very large to basically say that that yeah, they'll always, if you just fix some, yeah, firstly they'll always exist a 2 complex with x naught with fundamental group G and Euler characteristic 1. But what's more is there'll always exist a really large number of exotic presentations, i.e. non-cancellation examples for G. So, and there'll exist this super exponentially large number of exotic presentations. Okay, and this is using the assumption that G has the D2 property. Right. So just to go down to an example, so for the case of quaternion groups, the number of quaternionic representations is floor of n over 2 in this case. And so if Q4n has the D2 property, then you can derive, by plugging these things in, that the number of balanced presentations up to homotopy. So all of these presentations would be, exotic presentations, pairwise exotic. So the number of balanced presentations up to homotopy is always super exponential. Okay, for these quaternion groups as a consequence of this. But this sort of raises the question, so for these quaternion groups and for others, of where actually are all of these balanced presentations, right? So in the case of finite abelian groups, I gave explicit examples of presentations, but for these quaternion groups, where actually are they? So the D2 property predicts that an enormous number will exist. So sort of you would hope that there would be some construction, but there's none known. And this was until sort of recent results of Manon and Popiel in 2019, where they basically considered the simplest case, or one of the simplest cases, Q28, which has 3 H's, exactly the minimum number in its Wedderburn composition, and they basically found 2 exotic presentations over Q28. So you have the normal one, and then you have this kind of funny one. And I've also mentioned my name there. So what did I do? So all I did was I basically noted, using some of these other results, that in fact Q28 has the D2 property and there are no further presentations. Okay, but this is sort of, it still leaves open the case of, for n larger. So do these balanced presentations actually exist? It's sort of a strange thing that comes out of the theorem. Okay, and of course this is a potential way, and partly the point perhaps, to find a counterexample to the D2 problem. So can these things actually exist? If they can't, then you've proven that Q4n does not have the D2 property, and you found a counterexample to the D2 problem. Okay, so and the second consequence is for 4 manifolds. So recall that we had this construction which gives you takes 2 manifolds to 2 complexes to 4 manifolds. And with some additional work, it's basically possible to show the following. So suppose G has 4 periodic cohomology and the D2 property. Then if MH of G is sufficiently large, then you can always find 2 complexes X and Y with fundamental group G, for which X and Y are not homotopy equivalent, but the corresponding 4 manifolds are homotopy equivalent. And the proof of this is basically if MH of G is sufficiently large, then you just have such an enormous number of 2 complexes which are distinct up to homotopy, that when you go to the 4 manifolds through the boundary of thickenings construction, you just have so many 4 manifolds that the kind of the different algebraic invariants that classify them, there has to be some overlaps in the list because of the super exponential nature of the the number of 2 complexes you have. So it's a very indirect proof, sort of another sort of bizarre consequence. Okay, but again, this sort of assumes that G has the D2 property. So can we get rid of this assumption? So I'll just note the following, which gives you sort of some of the way there, which was shown very recently. I think maybe 3 weeks ago, I saw this posted on the archive. So there's a paper, some recent work by Adem and Hamilton, 2021. And they basically just extended the boundary of thickenings construction. They showed that it actually extends instead of having a map from 2 complexes to smooth 4 manifolds, you can have a map from D2 complexes to topological 4 manifolds instead. And using this, you can basically upgrade this result I just mentioned to the following. So namely, if M of H is sufficiently large, then there are always D2 complexes X and Y, which are not homotopy equivalent, but for which the corresponding topological, in this case, 4 manifolds, are homotopy equivalent. Okay. And I should mention, so these results, I've just put them as n dot, so they're not actually posted anywhere. That they're sort of, will appear in a later project, sort of will be incorporated in something larger. But if anyone wants to know more details, they're welcome to email me about that. Okay, So yeah, this is basically getting to the last slide. I'll just mention some further work. So we mentioned the cancellation problem for projective modules. In this particular case of 4 periodic cohomology, something I've been working on recently is basically the general case. So you can say that ZG has projective cancellation if you can always cancel off a free module, just in general. So i.e. if P has cancellation for all, the class of P has cancellation for all projective modules P. This has been open since the 1960s. I think Swan worked on it a lot between the 60s and 80s and got sort of partially far, but not quite the whole way. And I have a conjecture for the final form this classification should take. So if G is a finite group, then I conjecture that ZG will have projective cancellation if and only if G has no quotient H, which is of the following form. So if it has no quotient, which is a quaternionic group of sufficiently large order, it also has to have no quotient, which is one of these funny groups. So it's a semi-direct product of Q8 and SL2 of F3 to the power of N for a specific action. And additionally, sort of 14 exceptional groups of sort of increasingly bizarre orders. There is one of an order larger than the rest, order 1152, which is sort of like the monster in the family. Okay, so that's pretty much all I wanted to say. So I'll just conclude with a summary. So the first thing was that people should take away is that the homotopy classification of two complexes is only well understood in a few cases. So for example, when G is finite abelian. The second is that we can understand a lot about the case where G has 4 periodic cohomology by studying projective ZG modules. The third is that these results can be applied to solve Wald's Detour problem for several new families of groups. So maybe that's something I didn't point out very much, is that this is only really known in a few cases, sort of a few families of infinite groups, but these results give you many different infinite families for which the Detour property holds. And lastly, so the final thing was that if a Wald's Detour problem can be answered affirmatively, then you have the following consequences, which you might try and prove are not true in order to get a counterexample. So one is that you obtain a sort of reasonably complete homotopy classification of two complexes when G has 4 periodic cohomology. The second thing is that an extraordinary number, like an extraordinarily large number of exotic presentations must exist for groups such as the quaternions. And this is just despite the first examples only being found very recently. And in particular, these were some of the proposed counterexamples before, and people had tried to find these presentations before. And the third thing is that we can obtain many examples from this of two complexes which are not homotopy equivalent, but for which the corresponding four manifolds are. Okay, so sorry if I overran a little bit, but thank you for listening.
Okay, well, let's thank Johnny.